In today's lesson, we're going to look at the third and final type of distribution in this unit, and this is going to be a hypergeometric distribution. So again, it's going to be the same type of format as the previous lessons. We're going to look at a couple of examples. We're going to look at a specific formula in terms of probability, a specific formula in terms of expected value. We're going to look at how to use Google Sheets to make it a little bit easier for us in terms of creating a probability distribution table and a probability distribution graph. So again, same type of format, just a different distribution and different formulas. So as a warm-up, in a class of 25 students, 15 of them have a driver's license. If 5 students are randomly selected, how could we determine the probability that one of these students has their license, or 2 of them have their license, or we could extend it to 3 of them, 4 of them, or all 5 of them. So how would we do this? And we have come across some types of questions of this before when we looked at combinations. So just take a second to think about this. If you want to pause the video and try to solve this, you can, but we will look at this and kind of take it up using some new information. So this type of scenario is going to be our new distribution, or a new type of distribution, which we call hypergeometric. So a hypergeometric distribution involves dependent trials. Each of these trials has a success or failure, but it is dependent because the probability is going to change, or the things are going to change depending on what's occurring. Probability of success changes for every trial because no repetition is allowed. And in this case, the random variable is the number of successful trials. So this is what's unique about a hypergeometric distribution. And hopefully you can see the difference between this and the binomial distributions. So similar to binomial distributions and uniform distributions, we do have a specific formula to help us find the probability. Now it might look scary, but it's nothing that we haven't done before. It just might look a little scarier with a set formula. So and it's not 2 of them, it's 1 or the other. Just different representations based on how we may choose to represent our combinations. So basically it's saying the probability is equal to A choose X times N minus A choose R minus X over N choose R. And you're probably lost with all the letters, but we'll label each one. So starting with A. So A represents the number of total successful outcomes. X is the number of actual successes. R is equal to the number of dependent trials. And N is equal to the number of total outcomes. So hopefully when we look at some specific examples, this makes it a little bit easier to think about or to go through when we actually go through and do these calculations. But again, we will look at a way where we can do this in Google Sheets, so it makes it a lot easier to we only have to really do one calculation, and then it will create or auto-generate the rest. So let's go back, before we go back, the expected value formula for a hypergeometric distribution, a little bit easier. It's the expected value is equal to R times A divided by N. Again, R is the number of dependent trials, A is equal to the number of total successful outcomes and N is the number of total outcomes. So again, different expected value formula for a different type of distribution. So let's go back to that warm-up and go through finding the probability of each kind of scenario. So again, for our warm-up, we're looking for our A value, our X value, our R value, and our N value. Our A value is the number of total successful outcomes. So in this case, going back to the question, a success is a student, we're selecting a student with a license. So how many successful outcomes are there? In this case, there are 15 of them because there are 15 students with a driver's license. X for our number of outcomes, we're going to be looking at in our chart. We have them as 0, 1, 2, 3, 4, or 5 individuals. R is the number of dependent trials. So in this case, how many trials are we doing? And in this case, we are doing 5 of them. Right? We're selecting 5 students. N is the total number of outcomes. So how many possible students are there to choose? In this case, there are 25 possible students. So we should be able to get our A, our R, and our N from the question. Our X value we'd have to kind of interpret based on the fact that I'm selecting 5 students. I can have anywhere from 0 to 5 in terms of students who have a license. So using my formula then, the probability is going to equal, if we can look back at our formula, but A choose X, so 15 choose 0. Actually, let me zoom in a bit. 15 choose 0. So there's 15 students with licenses. I'm choosing none of them. Multiplying by N minus A, or 25 minus 15, or basically what it's saying is there are 10 students that do not have a license. And I'm going to be choosing R minus X, or 5 minus 0, or 5 of them, because it's for the 5 total students. And this is going to be divided by 25 choose 5, or the total number of possible outcomes. So we can see some similarities of how we might have reasoned through this. We'll worry about finding out the probabilities later. Actually, no, we'll do the first one now, and then we'll use that to confirm our first calculation on Google Sheets. So we should get that there are roughly 0.0047%. For outcome, or for there being one individual out of the 5 selected with a license, I'm going to represent this the different way. So we have 15 individuals choosing 1 that have a license times 10 individuals choosing 4 of them divided by 25 choose 5. And we can kind of see a pattern when we do it this way. 15 and 10 is 25, 1 and 4 is 5. So again, just a different way that we can visualize it or represent it. And this works out to 0.0593. Again, I'm not going to go through and calculate all of them because I'm just going to use but I'm going to use at least 2 of them to double check or just clarify that Google Sheets did do it correctly. So for 2, if we just want to go through it, we have 15 choose 2 times 10 choose 3 divided by 25 choose 5. 15 choose 3 times 10 choose 2 divided by 25 choose 5. 15 choose 4 times 10 choose 1 divided by 25 choose 5. And finally, 15 choose 5 times 10 choose 0 all divided by 25 choose 5. So those are the formulas that we should have, but I'm going to double check, or I'm going to do all the calculations on Google Sheets, and we'll go through a way of, again, showing you how to enter in this formula. This one might be a little bit trickier than the other one, but it is still doable. And that is why we have the first 2 examples to kind of reference and make sure that we've entered it correctly. So going back to Google Sheets, let me zoom in here. We have our table started with our columns. X, we're dealing with 1, 0, 1, 2, 3, 4, 5. And now we're going to enter in our formula. So let's just zoom in a bit more so we can see it clearly. So we're going to start off by hitting equals. We have a combination first. So the combination is going to be 15 choose X, which is going to be 0 in this case. We're going to multiply this by another combination. And in this case, our combination is going to be 10, comma, here's where it kind of gets a little bit tricky. It's going to be 5 minus X, because again, remember that part changes. And then we're going to divide it by another combination, 25 comma 5. So a couple things we needed to change. We can kind of do the calculations beforehand for figuring out, well, there's 15 successful outcomes. There are 10 unsuccessful, you could say. 5 minus X, and our combination that we're dividing by our total possible ways, 25 choose 5, isn't going to stay. We can see that we already have a formula, or the answer started, which does match what we were given. And now that that formula is in there, we can just click this blue square, drag it down, and double check our answers. So we can see the first 2 do match what we have, and for the rest of them, we can copy those answers now down into our notes if we needed to. Well, we're going to do it anyways. We'll round it because, again, we don't need all the decimal places. I'd say at least 3 or so. If we wanted to as well, if we needed to find the expected value, I can go through, same type of formula, first cell multiplied by the next one, hit equals, and then just drag it down. And again, this we can fill out into our table as well if we needed to. Keeping in mind, we can round as well. Because if we needed to find the expected number of students that we would select, or the expected number of students to have a license, we could determine that. If we needed to find our totals, just to clarify, double check, okay, the probabilities add up to 1, which is good. And here, our expected value works out to 3. So again, different ways we can do it. We could do it all by hand if we really wanted to. but it's sometimes easier to just use Google Sheets to help us kind of fast track those calculations. So we just filled out our table just for reference. Again, we did talk about using Google Sheets for this, going through, entering in our formulas, and just dragging it down to carry over. So let's kind of start to go through some other examples. So let's recall with combinations. So again, just looking at how we did, or how we can use this formula. So in Lotto 649, 6 numbers are chosen at random from 1 to 49. How many ways could you choose your numbers? Or in other ways, we're looking for our NS. So we have 49 numbers, we're choosing 6 of them. So we have 13,983,816 ways to select your numbers. B, to win second prize, you must match 5 of the 6 numbers. How many second prizes are possible? So this might be something similar to our our NA, if we were looking for the probability of winning second prize. So we have 2 parts here. We have our winning numbers, and we have our losing numbers. So for our winning numbers, I have 6 of them, and second place says I have to have 5 of them, so 6 choose 5, and then multiplied by how many losing numbers do I have? Well, I have 43 of them, and I'm going to choose 1 to be that 6th number. So I have 258 ways to match 5 numbers. And one thing we can notice, we can kind of see this pattern here. 6 plus 43 equals 49. And 5 plus 1 equals 6. So our first 2 numbers in our combinations have to add up to the total number of ways. Our last 2 numbers have to add up to how many trials you could say we're doing. And in this case, a trial would be selecting a number. So just some things you can think about as you go through this. Not B, but C. What is the probability of winning 3 numbers? So again, our probability of X is going to equal our NA over NS. If we wanted to use our formula, we could. X is going to be 3 in this case. Our A value, or the total number of successful outcomes is 6. Our R value for number of trials is 6. And our N value for the number of total outcomes is 49. And one thing to keep in mind, there are no repeats. So we're not repeating these numbers. But order doesn't matter. So in this case, for using our formula, 6 choose 3, 6 winning numbers, choosing 3 of them, multiplied by 43 losing numbers, choose 3 of them. Again, losing numbers, winning numbers. And that's what we divide by our total number of possible outcomes. So 49 choose 6. 246, 820 divided by 13,983,816, or works out to 0.018 or 1.8%. So therefore, there is a 1.8% chance of matching 3 numbers. So again, we've done this type of situation in our probability section of combinations, and it's the same formula that we're going to be using for a hypergeometric distribution. So in our next example, or our last example, we're going to look at a jury selection. And again, we'll go through this in multiple ways. We'll look at starting it off with at least coming up with the combinations or the formulas, and then we'll look at getting the actual calculations through Google Sheets. So determine the probability distribution for the number of women in a civil court jury, which is 6 jurors, selected from a pool of 8 men and 10 women. So a couple key things here: 8 men, 10 women. We're selecting 6 jurors in total, and we're looking for a probability distribution. So what is given to us in this question? First, what is our random variable? What is the x value going to represent? Or basically, what are we looking for? And in this case, we're looking for the number of women. So our random variable is going to be the number of women on the jury. So for our a value then, the total number of successful outcomes. In this case, it's going to be 10. So 10 is the total number of women that could be on the jury. X is going to be our random variable, which is anywhere from 0, 1, 2, 3, 4, 5, and 6, because those are all the different possible number of women on the jury. Because there's only 6 jurors selected, we can only have anywhere from 0 to 6 women on the jury. R, the total number of trials, or dependent trials, in this case is 6, which represents the number of jurors, the number of people selected. And then N is going to equal 18, the total number of possible outcomes, which in this case means the number of possible jurors, which is 8 men and women, so 18 individuals in total. So for my probability distribution, I should have for x 0 through 6, we're looking at number of women on the jury. So depending on which formula you use, you can use either one. But again, in general, it is a choose x times n minus a choose r minus x, all divided by n choose r. But you can think of it as that lottery question, right? The first part is looking at women, the second part is looking at men, and the bottom part is looking at the total. So you might want to use that as a way if the formula does seem intimidating. So if we look at it, for the first part, number of women, well, I have 10 women to choose from, but I'm choosing 0 in my first scenario, and I'm going to multiply that by men, which is 18 minus 10, or there's 8 of them, and I'm choosing 6 minus 0, or 6 of them, to make the 6 juries. Then I have 18 choose 6. This one I can calculate, just so I can have something to confirm. I get 0.0015. For the next example, I'll do this one in the other format, but I have 10 individuals, or 10 women, choosing one of them, multiplied by 8 males, choosing 5 of them, dividing by 18 total options, choosing 6 of them. And if I calculate it this way, not that it matters because it's just a different representation of the combination formula. And I can go through, and I am going to go through and just fill out what the calculation should be for the rest of them. Right? So we have 10 women choosing 2 of them, times 8 men choosing 4 of them, divided by 18 total options choosing 6. 10 choose 3, times 8 choose 3, divided by 18 choose 6. 10 choose 4, times 8 choose 2, divided by 18 choose 6. 10 choose 5, times 8 choose 1, divided by 18 choose 6. And lastly, 10 choose 6, times 8 men choosing none of them, divided by 18 choose 6. And this is what, and I could go through and calculate each one, and that would be the end of my probability distribution table. However, I'm not going to take the time to go through and calculate each one. I'm going to let Google Sheets do that for me. So again, going to Google Sheets, same kind of format. I have the expected value column set up as well, just for the next couple questions. But going through, we are looking at 0 women through 6. And now again, here's the tricky part for using Google Sheets. And that is that I want to make sure that I enter the formula correctly. So that's why whenever we have these questions, if you're using when you use Google Sheets, I am going to ask that you do one calculation by hand, just one so that I know that you know the formula, and 2 so that you have something to double check in Google Sheets, just to make sure or verify that you've entered it correctly, your formula. So again, starting off with equals, starting off with a combination. In this case, we have 10 women, and we're going to choose X amount. The X value I'm going to represent by the cell. I'm going to multiply that by another combination, which is going to be the 8 males, or the 8 men, and I am choosing, in this case, was it 6 minus X, and then I'm going to divide that by a third combination, which is the 18 choose 6. I'm going to go through 0.0015. That does work out, or does match up with what I've calculated by hand. So I should know that it works. I'm going to click the blue dot, drag it down. I can double check the third or the second one, which again does match up with what I have. And then we have the rest that we can then fill out into our table for reference to help us with the rest of the questions. 0.17, 0. So again, a lot easier to go through and just take your time to enter it in once in Google Sheets, and then carry it down to fill out the rest. We can double check our total just to make sure that it does add up to 1. which it does, so that's good. So that means we should be on the right track. So going back again to our table, hopefully we've gone through and we've filled out our probabilities. So that is our probability distribution table. For the graph, again, same as before. The y value is our px, our x value, or our x-axis is our individual outcomes. So here it's number of women, 0, 1, 2, 3, 4, 5, and 6 of them. If we wanted to, we can just say 0.1, 0.2, 0.3, 0.4. So going through, so for 0, use a different color. 0 is very small. For 1, it's 0.03. 2 is basically 1.7. 3 was 3 or 0.36. 4 was 0.31. 5 was 0.1 or 0.11. And 6 was 0.01. Say somewhere down there. So again, that's roughly what my probability distribution graph should look like if I'm doing it by hand. But again, we can also do it through Google Sheets. So again, I don't need the third column. I'm going to highlight the first two, insert, chart, and there we see our probability distribution graph. If anything, you don't need to worry about the titles, because they do technically still work. You may just want to change the labeling so that we can see the individual labels. But essentially there is our graph, and that does match roughly what we had or what we sketched. So again, regardless of how you choose to do it, probably easier to use Google Sheets for when you create the graph. But doing it by hand also works as well. It just won't be as accurate or as nice. B, what is the expected number of women on the jury? So here I'm going to use the expected value formula, and then I'll bring up Google Sheets again to help us go through that. So in this case, R is the total number of trials. So in this case, we have 6 trials, or basically 6 people we're selecting. We're going to multiply that by A, which is the number of successful outcomes, or the number of women, and divide that by how many individuals in total I have, or N. And when I do this, it works out to 0.33. So therefore, we expect to see, say, 3 or 4 women on the jury. Again, because it's kind of that decimal value. So you could argue one or the other in between there. 3 or 4 women is what we expect to see. Even if you just entered 3.33, that's fine as well. Just understanding that obviously we don't have 0.33 of an individual. If I wanted to go through and do this again in Google Sheets, I can. Again, probably a little bit quicker. Equals first column multiplied by the second column. drag down equals the sum, and I get 3.33 repeating. So again, if you're already doing a table in here, probably a quicker way to do this, but we do have the formula as well if you need to do it that way. One last example, looking specifically more at just the individual cases. A box contains 7 yellow, 3 green, 5 purple, and 6 red candies. What is the probability of getting 3 red candies among 5 candies? So in this case, again, I still want to figure out what's my variable. And my variable in this case is going to be the number of red candies. Or essentially you could say, what are you looking for? In this case, I'm looking for 3 red candies, so my variable is going to be just, in general, the number of red candies. My A value, how many successful outcomes are there? Well, there are 6 because there are 6 red candies. Number of red candies in total. My X value in this case is going to be 3 specifically because I'm looking for specifically 3 red candies. If it was a probability distribution, it would be different, but in this case I'm just looking at one case. My R value is going to be 5 because I'm choosing 5 candies. And N, or the total number of outcomes, is 21 because I have 21 total candies. So those are my variables that I am figuring out. You may not even need to go through and do that, but if you're sticking to the formula, then you may want to. So in this case, we have probability of, in this case, 3 is equal to, I'm going to use the one type of formula. I find this one a little bit easier to write out. But again, if we're a little bit confused on what these represent, again, the first one represents red candies, the second one represents other candies, and then we have our total underneath, which is what we're dividing by. So for red candies, I have 6 of them, and I'm choosing 3. Multiplied by the other candies, well, if there's 6, and I'm choosing 3, or sorry, I have 6 red out of 21, so that means there are 15 other candies. Choosing, or let's just go through and do the actual formula. So we have 21 minus 6. Choosing 5 minus 3, all divided by 21, choose 5. This does work out to then, can 6 choose 3, times 15 choose 2, divided by 21 choose 5. And when I go through and I calculate this, I should get 0.1032. Therefore, there is a 10.3% chance of selecting 3 red candies. Then lastly, B, what is the expected number of red candies among 5 candies poured from a box? In this case, I'm not doing a full probability distribution table, so I'm not going to use that sum of xpx. I'm going to use the formula specifically for hypergeometric distributions. In this case, my R value, or the number of trials, is 5, multiplied by A, which is 6 red candies, divided by the total number of possible outcomes, and I get 1.428. So therefore, we expect 1 or 2 red candies out of 5. So again, this last example was more or less using the formula to answer specific questions and not create a full distribution. If we had to create a full distribution, we could easily use Google Sheets or use these formulas for all the different scenarios from 0 red all the way up to 5 red candies. So again, the main things that we should have gotten from this lesson is understanding what a hypergeometric distribution is, understanding the characteristics of it, the formulas attached to it in both the probability and the expected value, as well as how to create a probability distribution table for this specific distribution, and using Google Sheets to help us or aid us in doing these calculations.